Tonight I want to tell you everything I know about Titan, because the more I learn about this place, the more I think it might be the most interesting world we've ever found. Not the most likely to harbor life, that distinction probably belongs to Europa or Enceladus. Not the easiest to reach, it takes 7 or 8 years to get there. Not the most dramatic, no erupting volcanoes like Io, no geysers like Enceladus. But the most interesting in the deepest sense. The most Earth-like in ways that are simultaneously familiar and profoundly alien. The place where the questions we ask are the biggest questions we know how to ask. No mountains, no seas, just a uniform, hazy, orange sphere. This is because Titan is wrapped in one of the most opaque atmospheres in the solar system, a dense, smoggy shroud of nitrogen and methane that scatters and absorbs visible light so effectively that the surface is completely hidden. This opacity frustrated astronomers for centuries. Titan was discovered by the Dutch astronomer Christian Huygens in 1655, the same Huygens whose name now adorns the only spacecraft ever to land there. Huygens spotted Titan as a point of light near Saturn and correctly identified it as a moon. But for the next 3 centuries, that's all anyone could say about it. It was a moon, a dot, a point of reflected sunlight with no discernible features. The atmosphere was discovered in 1944 by Gerard Kuiper, who detected methane absorption lines in Titan's spectrum. This was a startling discovery. No other moon in the solar system had a significant atmosphere. The moon doesn't. The Galilean moons of Jupiter don't, or at least their atmospheres are so thin as to be negligible. Titan's atmosphere was clearly substantial, and it contained methane, a gas that is destroyed by solar ultraviolet radiation over geological timescales. The presence of methane meant either Titan had some mechanism for replenishing it, or the methane was a temporary phenomenon that would eventually dissipate. We still don't fully know the answer to that question. I'll come back to it. But even with the knowledge of an atmosphere, Titan's surface remained invisible. The haze layer made of complex organic molecules called tholins formed when ultraviolet light breaks apart methane and nitrogen in the upper atmosphere and the fragments recombine into larger molecules is so thick that optical telescopes simply cannot penetrate it. Titan guards its secrets behind a curtain of chemistry. This changed when spacecraft arrived. And the story of spacecraft at Titan is one of the great narratives of planetary exploration. Pioneer 11 flew past Saturn in 1979 and passed within about 360,000 kilometers of Titan. It returned little useful data about the Moon. The instruments were not designed for detailed study of planetary atmospheres, but it confirmed that Titan was big, cold, and shrouded. The real revelations came with Voyager. Voyager 1 flew past Titan on November 12, 1980, at a distance of about 4,000 kilometers. This was a deliberate choice, and it was a choice that cost something. The Voyager 1 team specifically designed the Saturn flyby to include a close encounter with Titan because the scientific interest was so compelling, but the trajectory required for a close Titan flyby meant that Voyager 1 could not continue on to Uranus and Neptune. It was a one or the other decision, Titan or the outer planets. NASA chose Titan. This decision was based on the expectation that Voyager 1's cameras might be able to see through the haze, at least partially, and reveal Titan's surface. They couldn't. The images showed the same featureless orange ball that telescopes showed, just bigger and closer. The haze was too thick. Voyager 1's cameras operated in visible light, and visible light simply does not penetrate Titan's atmosphere. But Voyager 1 carried more than cameras. Its instruments measured Titan's atmospheric composition, temperature profile, and pressure, and the results were astonishing. The atmosphere was mostly nitrogen, not methane nitrogen, about 95% nitrogen with about 5% methane and traces of other hydrocarbons, ethane, propane, acetylene, hydrogen cyanide. This made Titan's atmosphere chemically more similar to Earth's than any other atmosphere in the solar system. Earth's atmosphere is 78% nitrogen. Titan's is 95%. The main difference is that Earth's atmosphere contains 21% oxygen and Titan's contains none. Instead, it has methane, which on Earth would be quickly destroyed by reaction with oxygen. The surface pressure was measured at about 1.5 atmospheres, 1.5 times Earth's sea level pressure. The surface temperature was about 94 Kelvin, minus 179 degrees Celsius. At this temperature and pressure, methane can exist as a liquid. This led immediately to speculation that Titan might have bodies of liquid methane on its surface, seas, lakes, even oceans. The idea of liquid methane on Titan was proposed by scientists at Caltech and Cornell in the early 1980s, shortly after the Voyager data was analyzed, but Voyager couldn't confirm it. The haze prevented surface observations. The existence of Titan's seas remained a hypothesis, a compelling, physically plausible hypothesis, but a hypothesis nonetheless for another 25 years. During those 25 years, technology caught up with ambition. Ground-based telescopes and the Hubble Space Telescope began observing Titan in infrared wavelengths that could partially penetrate the haze. These observations revealed for the first time crude maps of Titan's surface, bright and dark regions, some of which showed hints of being smoother or rougher than others. But the resolution was poor. Imagine trying to study the geography of Earth using only a few blurry pixels of infrared data. You might distinguish continents from oceans, but you couldn't identify a river or a lake. The mission that changed everything was Cassini-Huygens. Cassini-Huygens was a joint mission of NASA, the European Space Agency, and the Italian Space Agency. It was one of the most ambitious and successful planetary missions ever conducted. The Cassini orbiter arrived at Saturn in July 2004 and spent 13 years studying the Saturn system, the planet, its rings and its moons, before being deliberately plunged into Saturn's atmosphere in September 2017 to prevent any possibility of contaminating potentially habitable moons like Enceladus or Titan with terrestrial microorganisms. The Huygens probe, built by the European Space Agency, named after Titan's discoverer, was carried to Saturn aboard Cassini and released on December 25, 2004. On January 14, 2005, it entered Titan's atmosphere, deployed its parachutes, and descended through the haze for about 2 hours and 27 minutes, taking measurements and photographs all the way down. It landed on the surface and continued transmitting for about 72 minutes before its batteries died. Let me take you through that descent, because it remains one of the most extraordinary events in the history of space exploration, and it deserves to be experienced in detail. Huygens entered Titan's atmosphere at a speed of about 6 kilometers per second, roughly 13,000 miles per hour. It was protected by a heat shield that absorbed the friction of atmospheric entry, slowing the probe dramatically. At about 160 kilometers altitude, a drogue parachute deployed, pulling away the heat shield and exposing the probe's instruments to the atmosphere for the first time. At about 120 kilometers, the main parachute opened, a disc gap band parachute about 8.5 meters in diameter. Huygens began a slow, drifting descent through the upper atmosphere. The instruments started recording data immediately. What they found was a world of layered hazes, chemical complexity, and decreasing visibility. In the upper atmosphere, above about 200 kilometers, the haze was thin enough that some sunlight penetrated. Huygens's cameras could see the haze layers, parallel bands of smog, each one a different color and density, formed by different chemical processes at different altitudes. The scene was dim. Titan receives about 1% of the sunlight that Earth receives, because it's nearly 10 times farther from the sun, but it was not dark. Think of a heavily overcast day in winter. That's roughly the light level on Titan. As Huygens descended through the main haze layer, between about 150 and 50 kilometers, the probe's gas chromatograph mass spectrometer was sampling the atmosphere and analyzing its composition in real time. The results confirmed and extended the Voyager data: nitrogen, methane, traces of dozens of other organic molecules. Some of these molecules were complex, large hydrocarbons and nitriles that form through photochemistry in the upper atmosphere and then drift downward like a slow, invisible rain of organic particles. This organic rain is one of Titan's most remarkable features. Ultraviolet light from the sun strikes the upper atmosphere and breaks apart molecules of methane and nitrogen. The resulting fragments, reactive radicals of carbon, hydrogen, and nitrogen, recombine in various ways, forming increasingly complex molecules. These molecules aggregate into tiny particles, the tholins, that constitute the haze. Over millions of years, the tholins drift downward and accumulate on the surface, forming a layer of organic sediment that is, in chemical terms, extraordinarily interesting. Tholins are not a single compound. The term, coined by Carl Sagan and Bishun Khare in 1979, refers to a broad class of complex organic polymers, laboratory experiments that simulate Titan's atmospheric chemistry, passing ultraviolet light or electrical discharges through mixtures of nitrogen and methane, produce a reddish-brown, tar-like substance that contains amino acids, nucleotide bases, and other molecules relevant to biochemistry. The tholins on Titan's surface have never been directly sampled and analyzed, but if they're anything like the laboratory simulations, they represent a vast repository of prebiotic chemistry, the raw materials from which life could, under the right conditions, emerge. Carl Sagan himself was deeply fascinated by Titan. He considered it one of the most important targets for exploration in the solar system, precisely because of its organic chemistry. In a sense, Titan is a natural laboratory for studying the kinds of chemical processes that might have led to the origin of life on early Earth, but frozen in time, preserved at cryogenic temperatures, uncontaminated by the biological processes that long ago consumed Earth's prebiotic chemistry back to the descent. Below about 50 kilometers, Huygens dropped below the main haze layer and the surface began to become visible. This was the moment the world had been waiting for. After 350 years of looking at Titan's blank orange face, we were about to see what was underneath. The first images were noisy, limited in resolution, and took time to process. But as Huygens descended below about 30 kilometers, the pictures sharpened, and what they revealed was breathtaking: channels, branching dendritic channel networks, carved into a bright surface, looking for all the world like river drainage systems on Earth. Dark channels meandering through bright terrain, converging into larger channels, flowing toward a dark, flat lowland area. The pattern was unmistakable to anyone who has ever looked at a satellite image of Earth's river systems. These were river channels. Something had flowed through them, liquid, driven by gravity, carving channels through softer material, but not water at minus 179 degrees Celsius. Water is a rock. It's as hard as granite and forms the bedrock of Titan's surface. The liquid that carved those channels was methane, or possibly ethane, or a mixture of both. Liquid hydrocarbons flowing across a landscape of frozen water ice, carving drainage networks that look almost indistinguishable from terrestrial river systems. As Huygens descended further, more details emerged. The bright terrain appeared to be elevated, highlands of ice etched by the dark channels. The dark lowland area appeared to be flatter and smoother, possibly a dried lake bed or flood plain. The overall impression was of a landscape shaped by fluid erosion, with elevated source regions where rain or snowmelt collected and flowed downhill through valleys and channels to lowland basins. Rain on Titan, it rains methane. Let me be precise about this, because the meteorology of Titan is one of the most fascinating aspects of this world. On Earth, water evaporates from the oceans, rises into the atmosphere, cools, condenses into clouds, and falls as rain. This is the water cycle: evaporation, transport, condensation, precipitation. It drives weather, shapes landscapes, and sustains life. Titan has an analogous cycle, but with methane playing the role of water. Methane evaporates from the lakes and seas, rises into the atmosphere, is transported by winds, condenses into clouds, and falls as rain. The methane rain carves channels, fills lakes, and eventually evaporates again to repeat the cycle. The timescales are different. Titan's year is about 29 Earth years, so its seasons last roughly 7 Earth years each, and the methane cycle operates on correspondingly longer timescales. The rainfall is probably infrequent in most regions, not a daily drizzle, but perhaps an occasional downpour separated by years or decades of dry conditions. Some models suggest that methane rainstorms on Titan could be intense, brief, violent events that dump large quantities of liquid methane onto the surface, causing flash floods that reshape the landscape before the liquid drains or evaporates. There is evidence for this. The Cassini orbiter, during its 13 years at Saturn, observed changes on Titan's surface that appeared to be the result of rainfall. Dark patches appeared in equatorial regions after the northern spring equinox, consistent with rain wetting the surface and darkening it temporarily. Cloud outbursts were observed in the southern hemisphere during summer. The weather on Titan is real, it's dynamic, it changes, but I was describing the descent. Huygens continued to fall below about 10 kilometers. The surface features became increasingly clear. The probe was heading toward the dark lowland area. The camera images showed a relatively flat, featureless terrain, dark, with scattered, brighter spots that might have been cobbles or pebbles of ice. At about 8 kilometers, Huygens released its main parachute and switched to a smaller stabilizer drogue. This was intentional. The main parachute was slowing the descent so much that the probe's batteries would have died before reaching the surface. The smaller drogue allowed a faster descent, trading observation time in the upper atmosphere for time on the surface. The final moments of the descent were captured in images that I think are among the most haunting in the history of exploration. The ground approaching, slowly in dim orange light, a flat, moist-looking surface. No features visible, just a dark, smooth plain growing closer and then contact. Huygens hit the surface at about 4.5 meters per second, roughly 10 miles per hour. It didn't crash, it didn't bounce. The surface gave way slightly, like wet sand or a thin crust over softer material. The accelerometer data showed a brief deceleration consistent with the probe sinking about 10 to 15 centimeters into the surface before coming to rest. Huygens was on Titan. It was January 14, 2005. Humanity had landed on the most distant body it had ever touched. The probe's instruments immediately began characterizing the landing site. The gas chromatograph mass spectrometer detected a burst of methane, consistent with the probe's warm underside vaporizing methane from the surface material. The surface was wet with methane, not puddles, more like damp soil. The regolith at the landing site was saturated with liquid methane, the way beach sand is saturated with water just below the surface. The surface camera took a panoramic image that remains one of the most iconic photographs in space exploration. It shows a flat, dark plain strewn with rounded cobbles of water ice, pebbles and rocks scattered across the surface, their edges smoothed by some process, erosion by liquid methane, tumbling in a stream. Both are plausible. The cobbles are water ice, but they look like river rocks. The resemblance to a terrestrial gravel bed is uncanny. The light level at the surface was dim, about 1,000th the full sunlight on Earth. Comparable to a deeply overcast day or perhaps twilight, the sky was orange, the horizon was flat, the landscape was desolate, alien and strangely beautiful. Huygens transmitted data for about 72 minutes after landing, far exceeding its design requirement. The data was relayed through the Cassini orbiter to Earth. And then, as Cassini moved out of range and Huygens's batteries died, the transmission stopped. The probe went silent. It's still there, sitting on the surface of Titan, a dead machine on an orange plain, 1 billion miles from the people who built it. That landing remains, as of today, the most distant landing of a spacecraft from Earth. It is also the only landing ever conducted in the outer solar system. Every other surface landing in history has been in the inner solar system, on the Moon, Mars, Venus. Huygens went further by an enormous margin, and it worked. But Huygens was just one component of the Cassini mission. Over the next 13 years, the Cassini orbiter made over 100 close flybys of Titan, mapping its surface using radar that could penetrate the haze, imaging its atmosphere in multiple wavelengths, measuring its gravitational field, and building up the most comprehensive portrait of an alien world that has ever been assembled. And what Cassini revealed was extraordinary: the seas, the actual seas. Cassini's radar mapper, the synthetic aperture radar, or SAR, was able to see through Titan's haze by using microwave wavelengths that the tholins don't scatter. The radar images revealed Titan's surface in a resolution of a few hundred meters, not as sharp as the best Mars images, but sharp enough to see geological features, coastlines and bodies of liquid. The lakes and seas were found primarily in the northern hemisphere, concentrated in the polar regions. The largest Kraken mare is bigger than the Caspian Sea. Its area is about 400,000 square kilometers. Its depth is uncertain. Radar altimetry suggests it could be over 300 meters deep in some areas, though the measurements are challenging because liquid methane-ethane mixtures are partially transparent to radar at the frequencies Cassini used. Ligeia Mare, the second largest sea, is about 126,000 square kilometers, larger than Lake Superior. Punga Mare is smaller but still substantial, and scattered among these major seas are hundreds of smaller lakes, some just a few kilometers across, others tens of kilometers, filling depressions in the terrain like rain filling potholes. The composition of the seas has been estimated from spectroscopic data and modeling. They appear to be primarily liquid methane, with significant amounts of dissolved ethane and smaller quantities of dissolved nitrogen. The nitrogen dissolution is important because it affects the density and behavior of the liquid. Nitrogen-rich methane is slightly less dense and more volatile than pure methane, which has implications for how the seas interact with the atmosphere. The seas have shorelines, they have bays and peninsulas and islands. Some of the shoreline features are remarkably similar to terrestrial coastal morphology: drowned river valleys, fjord-like inlets, smooth beaches. Cassini's radar images revealed features that planetary geologists immediately recognize as familiar, despite being made of completely unfamiliar materials. The seas also have, and this took years to confirm, waves. In Cassini's later years, as the sun moved northward and sunlight reached the northern seas for the first time in decades, the radar data showed what appeared to be surface roughness on Ligeia Mare and Punga Mare. The roughness was consistent with small waves, perhaps a centimeter or two in height, tiny ripples on a methane sea. Think about what that means. Waves require wind. Wind requires an atmosphere with density and dynamics. The fact that Titan's seas have waves means that the atmosphere interacts with the liquid surface in the same fundamental way that Earth's atmosphere interacts with Earth's oceans. Wind blows across the surface, friction transfers energy from air to liquid, and the energy manifests as waves. The physics is identical. The materials, nitrogen air instead of nitrogen oxygen air, methane liquid instead of water, are different, but the process is the same. This is one of the deep themes of Titan science. The processes are Earth-like, the materials are alien, and the combination of familiar processes with alien materials creates a world that is simultaneously recognizable and foreign, comfortable and disturbing, like a dream of Earth written in a different chemical language. The dunes, I haven't talked about the dunes yet, and they're remarkable. Cassini's radar revealed that Titan's equatorial regions are covered in vast fields of longitudinal dunes, parallel ridges of dark material, extending for hundreds of kilometers, oriented roughly east-west. The dune fields are enormous. They cover about 12% of Titan's surface, concentrated in a broad belt around the equator. The dunes are typically about 1 to 2 kilometers apart, about 100 meters tall, and tens to hundreds of kilometers long. On Earth, longitudinal dunes, also called linear dunes or Seife dunes, form when wind blows consistently from one direction or alternates between two directions. The sand organizes itself into parallel ridges aligned with the prevailing wind. The Namib Desert, the Australian outback, parts of the Sahara, all have longitudinal dunes formed by the same process. Titan's dunes are formed by the same process but with very different sand. The sand on Titan is not silicate, it's organic. It's composed of the tholins that rain down from the upper atmosphere, accumulating on the surface over millions of years, and then being shaped by wind into dune fields. The individual grains are tiny, perhaps a fraction of a millimeter in diameter, and they're made of complex hydrocarbons and nitriles. Imagine walking on a beach where the sand is made of plastic-like organic particles instead of quartz grains. That's roughly what Titan's dune fields are. The wind patterns that shape the dunes are not fully understood. General circulation models of Titan's atmosphere predict westward winds at the equator, but the dunes appear to indicate eastward transport. This discrepancy, known as the Titan dune paradox, has generated significant discussion. One possibility is that the dunes are shaped not by the prevailing winds, but by rare, intense storms that produce brief but powerful eastward gusts. Another is that the relationship between wind direction and dune orientation is more complex on Titan than simple models suggest. The dune fields are equatorial, while the seas are polar. This geographic distribution tells us something about Titan's climate. The equatorial regions are apparently drier, less methane rainfall, more evaporation, while the polar regions are wetter, accumulating enough liquid methane to fill large basins. This is analogous to Earth, where tropical regions tend to have more evaporation and polar regions tend to have more precipitation and ice accumulation. The mechanisms are different on Earth. The relevant variable is water. On Titan, it's methane, but the climate patterns are recognizably similar. Let me now talk about what's under Titan's surface, because this is where the story gets genuinely wild. Cassini measured Titan's gravitational field with extraordinary precision. By tracking the Doppler shift of Cassini's radio signal during close Titan flybys, scientists could measure how the spacecraft's velocity changed as Titan's gravity pulled on it. These velocity changes revealed the distribution of mass inside Titan, and the results were surprising. The gravitational data, combined with measurements of how Titan's shape responded to Saturn's tidal forces, strongly suggested that Titan has a global subsurface ocean of liquid water lying perhaps 50 to 100 kilometers beneath the icy surface. This is not a small amount of water. If the models are correct, Titan's subsurface ocean may contain more liquid water than all the oceans on Earth combined. The ocean is probably salty mixed with ammonia, which acts as an antifreeze, keeping the water liquid at temperatures that would otherwise freeze it solid. The ammonia water solution is sandwiched between an outer shell of water ice and an inner layer of high-pressure ice that rests on top of Titan's rocky core. The evidence for this ocean comes from several independent measurements. First, the tidal response. Titan's shape changes measurably as it orbits Saturn, flexing in response to Saturn's tidal forces. The degree of flexing is too large to be explained by a solid body. It requires a liquid layer that allows the outer shell to deform more easily. Second, the rotation rate. Titan appears to rotate slightly faster or slower than synchronous, which would be unusual for a solid body tidally locked to Saturn, but is expected if the surface is decoupled from the interior by a liquid layer. Third, the gravitational field. The mass distribution inside Titan is consistent with a layered structure that includes a liquid layer. So Titan has two types of liquid. On the surface, methane and ethane. Below the surface, water. Two completely different chemical systems separated by tens of kilometers of water ice. Each system, in its own way, represents a potential habitat for some form of chemistry or biology. And this is where the question of life on Titan becomes genuinely interesting and genuinely complicated. When astrobiologists talk about life on icy moons, they usually focus on the subsurface oceans, Europa's ocean, Enceladus's ocean, and now Titan's ocean. The idea is that liquid water, chemical energy, and the right ingredients could support microbial life in these hidden seas. Just as microbial life thrives in the deep oceans of Earth, Titan's subsurface ocean is a candidate for this kind of life, water-based life using biochemistry similar to what we know on Earth. But the ocean is deeply buried and very cold, and we know almost nothing about its chemistry. The conditions might be right for life, they might not. We simply don't have enough data to say. But Titan offers something that no other world does, a second, completely different environment where life might exist. The surface, the methane lakes, the tholin-covered terrain. What if life could exist, not in water, but in liquid methane? This idea sounds crazy at first. Life as we know it depends on water. Water is the solvent in which all terrestrial biochemistry occurs. Proteins fold in water, DNA replicates in water. Cells are bags of water containing complex chemistry. To suggest that life could exist in liquid methane is to suggest a fundamentally different kind of biochemistry, one that has no precedent on Earth. But there are serious scientists who take this idea seriously, and their arguments are worth understanding. The key question is whether liquid methane can serve as a biochemical solvent, whether it can dissolve complex molecules, facilitate chemical reactions, and provide the medium for some form of self-organizing chemistry. Water is an excellent solvent because it's polar. The water molecule has a positive end and a negative end, which allows it to interact strongly with other polar and ionic molecules, dissolving salts, sugars, amino acids, and the myriad other molecules of life. Methane is non-polar. It doesn't dissolve salts or sugars. The molecules that dissolve in liquid methane are very different from the molecules that dissolve in water. This doesn't mean chemistry can't happen, it means different chemistry happens. Lipids, for example, are soluble in non-polar solvents. Complex organic molecules like the tholins on Titan's surface might dissolve or interact in liquid methane in ways that could lead to some form of chemical complexity. In 2015, a group at Cornell University, led by chemical engineer Paulette Clancy and including James Stevenson and Jonathan Lunine, published a paper proposing a hypothetical cell membrane that could function in liquid methane on Earth. Cell membranes are made of phospholipids, molecules with a polar head and non-polar tails. In water, these molecules spontaneously arrange themselves into bilayer sheets, with the polar heads facing the water and the non-polar tails facing each other. This forms the membrane that encloses every living cell. In liquid methane, phospholipid membranes wouldn't work. The chemistry is reversed. But the Cornell group proposed that small nitrogen-containing organic molecules called azotosomes could form analogous membrane structures in liquid methane. The azotosome membranes would be inside out compared to terrestrial membranes, with the non-polar portions facing the liquid methane solvent and the polar portions facing inward. But they could in principle form enclosed vesicles that might serve as compartments for chemical reactions, the methane equivalent of cells. This is theoretical. Nobody has built an azotosome. Nobody has demonstrated that they spontaneously form in liquid methane. The idea is a hypothesis, a scientifically grounded hypothesis, but a hypothesis nonetheless. It tells us that methane-based life is not physically impossible. It doesn't tell us that it exists. But here's what makes Titan so compelling in this context. If methane-based life does exist anywhere, Titan is where we'd find it. It's the only world we know of that has stable bodies of liquid methane on its surface, with a supply of complex organic molecules raining down from the atmosphere and enough energy from cosmic rays, from radioactive decay in the interior, possibly from chemical energy sources we haven't identified, to drive some form of metabolism. And there are hints, tantalizing, ambiguous hints, that something unusual might be happening on Titan's surface. In 2010, 2 papers were published that, taken together, suggested something was consuming hydrogen and acetylene near Titan's surface. One paper by Darrell Strobel showed that hydrogen was flowing downward through Titan's atmosphere and disappearing at or near the surface. On a world with no biology, hydrogen should accumulate at the surface or react slowly with surface materials. Something was removing it. The other paper by Roger Clark showed that acetylene, one of the most abundant organic molecules produced in Titan's upper atmosphere, was present at the surface in much lower concentrations than expected. Acetylene is thermodynamically the most efficient fuel available in Titan's environment. If you react acetylene with hydrogen, you release energy. A hypothetical methanogenic organism on Titan could, in principle, metabolize acetylene and hydrogen, releasing methane as a waste product, the reverse of what methanogens on Earth do, which consume hydrogen and carbon dioxide and produce methane. When these 2 papers were published, some media outlets ran headlines suggesting that life had been discovered on Titan. It hadn't. The observations are consistent with life, but they're also consistent with purely abiotic processes, unknown catalytic chemistry on the surface, reactions with mineral phases we haven't characterized, or simply errors in the models. The signal is suggestive but far from conclusive. Chris McKay, a planetary scientist at NASA Ames and one of the leading thinkers on Titan astrobiology, put it well. He said that the hydrogen and acetylene observations are exactly what you'd expect to see if there were methane-based life on Titan. But they're also consistent with many non-biological explanations. To distinguish between these possibilities, you need more data. Specifically, you need data from the surface, which brings us to Dragonfly. Dragonfly is a NASA mission that will send a robotic rotorcraft, essentially a nuclear-powered drone, to Titan's surface. It was selected as the 4th mission in NASA's New Frontiers program in June 2019. It is, by any measure, one of the most audacious planetary missions ever conceived. Let me describe what Dragonfly is and what it will do, because the engineering is extraordinary. Dragonfly is an octocopter, a rotorcraft with 8 rotors arranged in 4 pairs on 4 arms extending from a central body. It's about 3 meters long and about 1 meter tall, with a mass of about 450 kilograms. It looks roughly like a large consumer drone, but built to survive conditions that would destroy any consumer drone in seconds. The rotorcraft design is possible because of Titan's unique combination of atmospheric density and low gravity. Titan's atmosphere is about 4 times denser than Earth's at the surface. Titan's gravity is about 1/7 of Earth's, close to the Moon's gravity, actually. The combination means that generating aerodynamic lift on Titan is remarkably easy. A rotor on Titan doesn't need to work as hard to support a given mass as it would on Earth. The thick atmosphere provides more lift per unit of rotor area, and the low gravity means less weight to support. Dragonfly's rotors will spin at about a few hundred RPM, much slower than a terrestrial drone's rotors, because the thick atmosphere provides ample lift at lower speeds. The flights will be relatively sedate by Earth drone standards, low altitude, moderate speed, but each flight will cover several kilometers, and over the course of the mission, Dragonfly is expected to travel a total of over 170 kilometers. That's further than any rover has driven on Mars. Curiosity has covered about 32 kilometers in 12 years. Perseverance has covered about 28 kilometers in 4 years. Dragonfly will cover 170 kilometers by flying, hopping from site to site, spending time on the ground at each location to conduct science, then lifting off and flying to the next. The power source is a multi-mission radioisotope thermoelectric generator, an MMRTG, the same type of nuclear battery that powers the Curiosity and Perseverance rovers on Mars. It generates electricity from the decay of plutonium-238, producing about 70 watts of electrical power continuously. This is not enough to power the rotors directly. Flying requires far more power than 70 watt. Instead, the MMRTG charges a lithium-ion battery during the long periods when Dragonfly is on the ground. When the battery is fully charged after a Titan day, which is about 16 Earth days, Dragonfly takes off, flies to its next destination, lands, and begins recharging for the next flight. The use of nuclear power is essential. Solar panels are essentially useless at Saturn's distance from the Sun. They would need to be enormous to generate meaningful power, and Titan's hazy atmosphere would further reduce their output. An MMRTG works regardless of sunlight. It generates power from radioactive decay 24 hours a day in any environment. It's the same technology that has kept Voyager's instruments running for nearly 50 years. Dragonfly's instrument suite is designed to characterize Titan's surface chemistry and search for signs of prebiotic chemistry or biological activity. The key instruments include a mass spectrometer that will analyze surface material and atmospheric samples, a gamma-ray spectrometer that will measure the elemental composition of the surface, a meteorological package that will measure temperature, pressure, humidity, and wind, and cameras that will document the landscape at each landing site. The mass spectrometer, called DRAMS for Dragonfly Mass Spectrometer, is particularly important. It's derived from the sample analysis at Mars instrument on Curiosity and is designed to identify complex organic molecules in Titan's surface material. It can detect amino acids, nucleotide bases, and other molecules relevant to biochemistry. If the tholins on Titan's surface contain prebiotic molecules, and laboratory simulations strongly suggest they do, DRAMS will find them. The mission plan calls for Dragonfly to land initially in an equatorial dune field, then gradually make its way, flight by flight, toward a large impact crater called Selk Crater. Impact craters are scientifically interesting on Titan for a specific reason. When a large impactor strikes Titan's surface, the impact energy melts the water ice bedrock, creating a temporary pool of liquid water on the surface. This transient water interacts with the tholin material on the surface, the complex organic molecules that have been raining down from the atmosphere for millions of years. The combination of liquid water and complex organics in a warm environment is exactly the kind of setting where prebiotic chemistry might advance toward greater complexity. Silk Crater is about 80 kilometers in diameter. The impact that formed it melted the ice and created conditions, possibly lasting centuries or millennia, where liquid water and organic molecules coexisted. If any prebiotic chemistry occurred as a result, the products might still be preserved in the crater floor. Dragonfly will fly to Silk Crater, land on its floor, and analyze the surface material with drones. This is the most direct search for prebiotic chemistry, and possibly for signs of life, that has ever been conducted on a world other than Mars. The mission timeline is, and this requires patience, long. Dragonfly was originally planned for launch in 2026, with arrival at Titan in 2034. The launch has been delayed to July 2028, with arrival now expected in 2034. The delay was due to a combination of budget pressures, COVID-related disruptions, and technical challenges. 8 years of flight. Think about that. Dragonfly will launch from Earth in 2028 and spend 8 years coasting through the solar system, using gravity assists from Venus and Earth to build up enough velocity to reach Saturn. It will arrive at the Saturn system in approximately 2034, enter Titan's atmosphere directly, no orbital insertion, and descend to the surface under parachute before engaging its rotors for the final landing. The Dragonfly team will spend those 8 years preparing for surface operations, training operators, refining flight plans, and waiting. 8 years of waiting for a spacecraft that is already built, already launched, already on its way, but not yet at its destination. The patience required for outer solar system missions is extraordinary. The Cassini team waited 7 years for their spacecraft to reach Saturn. The New Horizons team waited 9.5 years for their spacecraft to reach Pluto. These are the timescales of deep space exploration. They demand a kind of institutional endurance that is rare in human organizations. And here I want to talk about something that most discussions of Titan don't address, but that I think is fundamental. The question of Titan's methane. Here is the problem. Methane is destroyed in Titan's upper atmosphere by solar ultraviolet radiation. The UV light breaks apart methane molecules, and the fragments recombine to form more complex hydrocarbons, ethane, propane, acetylene, and eventually the tholins. This destruction is continuous and irreversible. Once methane is converted to ethane or acetylene, it doesn't spontaneously convert back. The process goes only one way. At the current rate of destruction, all of Titan's atmospheric methane should be destroyed in about 10 to 30 million years. That sounds like a long time, but Titan is 4.5 billion years old. If methane has been present in the atmosphere for the entire history of the solar system, it should have been destroyed and replenished hundreds of times over. This means either Titan has a source of methane that continuously resupplies the atmosphere, or the methane is episodic, present during some periods and absent during others. The source of Titan's methane is one of the biggest unsolved problems in planetary science. Several hypotheses have been proposed. The most commonly cited is outgassing from the interior, methane stored in Titan's crust or mantle, released through volcanic processes, cryovolcanism in Titan's case, involving eruptions of water-ammonia mixtures rather than molten rock. If Titan has methane-rich clathrates in its ice crust, cage-like structures of water ice with methane molecules trapped inside, warming or disruption of these clathrates could release methane into the atmosphere. Another hypothesis involves the subsurface ocean. If the ocean contains dissolved methane, or if methane is produced by chemical reactions between the ocean water and the rocky core, a process called serpentinization, which occurs on Earth at mid-ocean ridges, methane could gradually percolate upward through the ice crust and into the atmosphere. A third hypothesis, more speculative, involved biological production. If methanogenic organisms exist in Titan's subsurface ocean, they could produce methane as a metabolic waste product, just as methanogens on Earth produce methane in swamps, rice paddies, and the guts of cows. This methane could diffuse upward through the ice and replenish the atmosphere. It's a seductive idea. Titan's methane is a biosignature, evidence of life hidden in a subsurface ocean, but it's entirely unproven and probably untestable with current technology. The truth is probably some combination of geological processes. Cryovolcanism and clathrate destabilization are the most widely accepted explanations, but the specific mechanism remains uncertain, and the rate at which methane is replenished is not well constrained. This uncertainty affects everything we think we know about Titan's climate history. If methane has been continuously present for billions of years, then Titan has had its current climate, with methane rain, lakes, and a thick atmosphere for most of its history. The surface has been shaped by methane erosion for eons, and the tholin deposits could be incredibly deep. If methane is episodic, present for some periods and absent for others, then Titan's climate may have fluctuated dramatically over geological time. During methane-free periods, the atmosphere would be much thinner, the surface would be colder. There would be no rain, no rivers, no lakes. Titan would look very different. The current landscape might be the result of relatively recent methane replenishment, with older terrain buried beneath the current surface features. We don't know which scenario is correct. Dragonfly may help answer this question. The depth and composition of the tholin deposits, the erosion state of the terrain, the isotopic composition of the atmospheric methane, all of these could provide clues about the long-term stability of Titan's methane cycle. Let me talk about the landscape more broadly, because Cassini revealed a world of extraordinary geological diversity mountains. Titan has mountains of water ice, reaching heights of perhaps 1 to 2 kilometers above the surrounding terrain. These are not impressive by Earth standards, let alone by the standards of Olympus Mons on Mars, but they're significant on a world with a relatively young, geologically active surface. The mountains appear to be formed by tectonic processes, compressional folding, thrust faulting, driven by forces that are not fully understood, but may be related to tidal stresses from Saturn, thermal contraction of the interior, or convective motions in the ice crust, cryovolcanoes. The evidence for cryovolcanism on Titan is suggestive but not conclusive. Several surface features have been identified that resemble volcanic constructs, elevated areas with flow-like features emanating from central vents. The most prominent is a feature called Sotra Patera, which has a deep pit, elevated flanks, and what appear to be flow deposits. If Sotra is a cryovolcano, it would imply that Titan's interior is warm enough to produce water ammonia magma and erupt it onto the surface. This would be consistent with the internal ocean model and would provide a potential mechanism for methane release. But proving cryovolcanism from orbital data alone is difficult. The resolution of Cassini's instruments was not always sufficient to distinguish volcanic features from other geological formations. Definitive evidence may require surface exploration, another task for Dragonfly or its successors, impact craters. Titan has surprisingly few impact craters, far fewer than would be expected for a world that has been exposed to bombardment for 4.5 billion years. The Moon, Mercury, Callisto bodies of similar age are saturated with craters. Titan has perhaps 60 or 70 confirmed or probable craters, and most of them are degraded, partially filled, eroded, or buried. This paucity of craters tells us that Titan's surface is geologically young, that some process or combination of processes is continuously erasing craters. The candidates are familiar from Titan's repertoire: erosion by methane rain, burial by tholin deposits, tectonic deformation, cryovolcanic resurfacing. All of these can destroy craters over time. The fact that the surface is so young, perhaps hundreds of millions of years old in many areas, not billions, means that Titan is an active world, continuously reshaping itself. The polar regions have their own distinct character. In addition to the seas and lakes, the North Pole has extensive areas of labyrinthine terrain, networks of narrow valleys and sharp ridges that resemble karst topography on Earth. Karst forms on Earth when soluble rock, limestone typically, is dissolved by acidic water, creating sinkholes, caves, and complex drainage networks. On Titan, the analogous process might involve methane dissolving the organic surface material, creating similar dissolution features. The South Pole is different. It has fewer and smaller lakes than the North. This asymmetry, more liquid in the North, less in the South, is probably seasonal. Titan's orbit around Saturn is slightly eccentric, which means the southern hemisphere summer is shorter but more intense than the northern summer. This causes more evaporation in the south and more net transport of methane to the north. Over long timescales, hundreds of thousands of years, the asymmetry may reverse as Saturn's orbital parameters change. I want to return now to the atmosphere because its chemistry is remarkable in ways I haven't fully described. Titan's atmosphere is a chemical factory. Ultraviolet light from the sun, cosmic rays from deep space, and energetic particles from Saturn's magnetosphere all provide energy that drives chemical reactions in the upper atmosphere. These reactions transform simple molecules, methane, nitrogen, hydrogen, into complex ones. The chemistry is extraordinarily rich. Over 100 distinct molecular species have been identified in Titan's atmosphere by various instruments. The list includes simple hydrocarbons like ethane, ethylene, acetylene, and propane. It includes nitriles, molecules containing carbon-nitrogen bonds like hydrogen cyanide, cyanoacetylene, and dicyanoacetylene. It includes more exotic species like benzene, toluene, and even more complex aromatic compounds. The presence of nitrogen in the chemistry is particularly significant. Nitrogen is essential for biology as we know it. It's a key component of amino acids, proteins, and nucleic acids. On Earth, atmospheric nitrogen is biologically inert. Organisms can't use it directly. It must first be fixed, converted into reactive compounds like ammonia or nitrate by specialized bacteria or by lightning. On Titan, the chemistry of the upper atmosphere does this work automatically, producing nitrogen-bearing organic molecules that rain down onto the surface. Titan's surface is bathed in a steady supply of nitrogen-containing organics, exactly the kind of molecules that, in a liquid water environment, could participate in prebiotic chemistry. This is the connection between Titan's atmospheric chemistry and the question of life's origins. On early Earth, before life began, the atmosphere probably contained methane, nitrogen, carbon dioxide, and water vapor, a mix not entirely unlike Titan's, though with different proportions. The Miller-Urey experiment of 1953, which demonstrated that amino acids could be produced by passing electrical discharges through a mixture of methane, ammonia, hydrogen, and water, was essentially an experiment in Titan chemistry plus water on Titan. The atmospheric chemistry produces the organic building blocks continuously. The missing ingredient is liquid water, which is present only beneath the surface in the subsurface ocean or transiently in impact craters where the ice is melted. The question is whether the organic molecules produced in the atmosphere ever encounter liquid water on the surface, and if so, what chemistry results. Selk crater, Dragonfly's target, is a place where this encounter happened. An impact melted the ice, creating a temporary pool of liquid water surrounded by organic rich surface material. For a time, maybe centuries, maybe millennia, water and organics coexisted. What happened during that time? Did the organics dissolve in the water? Did they react? Did they form more complex molecules, amino acids, peptides, nucleotide bases? Did they take steps toward the kind of chemical complexity that on Earth eventually led to life? We don't know. But Dragonfly will go there and look. Let me now zoom out and compare Titan to the other worlds in our solar system that we consider potentially habitable, because Titan occupies a unique position in this landscape. Europa, Jupiter's moon, has a subsurface ocean of liquid water beneath an ice shell. The ocean is in contact with a rocky sea floor where hydrothermal vents could provide energy and minerals. It's perhaps the most promising place in the solar system to search for extraterrestrial life if we define life as water-based microbiology, similar to Earth's. Enceladus, Saturn's small moon, also has a subsurface ocean, and it's easier to sample because Enceladus actively jets ocean material into space through cracks in its south polar ice. The Perseverance rover is collecting samples for eventual return to Earth, where they can be analyzed for biosignatures. Mars is the most accessible, potentially habitable world, and it gets the most attention and funding. Titan is different from all of these. It's not better or worse, it's different. Its potential habitability is not based on its similarity to Earth, but on its dissimilarity. Titan challenges us to think about life in a fundamentally different way. Not water-based life, but methane-based life. Not biochemistry we recognize, but biochemistry we can barely imagine. If we find life on Europa or Enceladus, it will probably look biochemically familiar, using water as a solvent, perhaps using DNA or RNA or something analogous. If we find life on Titan's surface, it will be alien in a much deeper sense, using different chemistry, different solvents, different metabolic pathways. Finding water-based life on Europa would tell us that Earth-like life can arise independently. That's important. Finding methane-based life on Titan would tell us that life can arise in forms we've never imagined. That's transformative. It would mean that the universe is not just teeming with life, it's teeming with kinds of life, different chemistries, different solvents, different environments, all producing self-organizing systems that we would recognize as alive. The implications for the abundance of life in the universe would be staggering. This is why I said at the beginning that Titan might be the most interesting world we've ever found. Not because it's most likely to harbor life, it probably isn't compared to Europa or Enceladus, but because if it does harbor life, the discovery would rewrite our understanding of biology itself. Let me tell you about the seasons on Titan, because they're important for understanding the climate and because they're beautifully strange. Titan orbits Saturn, and Saturn orbits the Sun with a period of about 29.5 Earth years. Saturn's axial tilt, about 27 degrees similar to Earth's, means that both Saturn and Titan experience seasons. Each season on Titan lasts about 7 to 7.5 Earth years. When Cassini arrived at Saturn in 2004, it was early southern summer on Titan. The sun was high in the southern sky. The southern hemisphere received the most solar energy, and weather patterns reflected this. Clouds were observed primarily in the south. Over the 13 years of the Cassini mission, the seasons progressed from southern summer through equinox in August 2009 into northern spring. By the end of the mission in 2017, clouds were beginning to appear in the north, and the northern seas were emerging from decades of polar darkness into their first sunlight in nearly 15 years. The seasonal changes on Titan are not just shifts in sunlight, they drive real changes in weather and surface conditions, The methane cycle responds to seasonal forcing. During summer in a given hemisphere, more solar energy reaches the surface, driving evaporation from the lakes and seas. The methane vapor is transported through the atmosphere and eventually precipitates, but not necessarily in the same hemisphere. The atmospheric circulation patterns can transport methane across the equator, leading to rain in the winter hemisphere. The equinox period is particularly interesting. Around equinox, the atmospheric circulation shifts and large-scale disturbances, storms, can occur. In 2009 and 2010, Cassini observed dramatic cloud outbursts near the equator that appeared to produce significant rainfall. The dark patches that appeared in equatorial regions after these outbursts were consistent with wet surfaces, methane rain darkening the tholin-covered terrain. These observations suggest that Titan's equatorial regions, which are currently dominated by dunes and appear relatively dry, may experience episodic heavy rainfall during equinox periods. The rainfall events may be intense, large volumes of methane falling in short periods, and may be responsible for carving the channel networks observed by Huygens during its descent. The channels might not be continuously active rivers, but intermittent flood channels that activate during rare storm events, similar to the wadis of Earth's deserts when Dragonfly arrives in the mid-2030s. It will be northern summer on Titan. The northern seas will be fully illuminated and the climate will be in a different state from what Cassini observed during its first few years. Dragonfly will have an opportunity to study Titan's climate during a different seasonal phase, providing complementary data to Cassini's observations and helping to build a more complete picture of the methane cycle. Let me talk about the sound of Titan, because this is something that I find irresistibly evocative. Titan is the only world in the outer solar system where sound travels through a thick atmosphere. On the Moon, there's no atmosphere, no sound. On Mars, the atmosphere is so thin that sound is faint and travels poorly. But on Titan, the atmosphere is dense, denser than Earth's, and sound travels efficiently. However, the speed of sound on Titan is different from Earth. The low temperature means the gas molecules move more slowly, and the higher molecular weight of Titan's atmosphere, dominated by nitrogen, but with significant methane, further reduces the speed of sound. Sound on Titan travels at about 194 meters per second, compared to about 343 meters per second on Earth. Sounds on Titan would be lower pitched, more muffled, and would propagate more slowly. If you could stand on Titan's surface in a heated spacesuit with a breathing apparatus and listen, you would hear the wind. The wind on Titan is generally light at the surface. Models predict speeds of a meter per second or less, but it's not zero. You would hear a faint, low hissing or murmuring as the dense nitrogen-methane atmosphere moved past your helmet. You might hear the crunch of tholin-coated ice beneath your boots. If you were near one of the seas, you might hear waves, small waves, lapping gently against an icy shore. The Huygens probe carried a microphone, or rather, an acoustic sensor package designed to measure atmospheric properties, including sound, during the descent. It recorded the sound of the probe descending through Titan's atmosphere. The recording is not dramatic. It's a low, steady drone, a combination of wind noise and instrument vibrations. But it's a real sound from a real alien world, and I find it hypnotic. Dragonfly will carry better acoustic instruments, and the sound of its rotors beating through Titan's thick atmosphere will be recorded and transmitted to Earth. The sound of a human-made drone flying through the atmosphere of a moon of Saturn, I don't know what that will sound like. Nobody does, but I want to hear it more than I want to hear almost anything. There's a philosophical dimension to Titan that I think is worth exploring, even if it takes us into territory that's more speculative than usual. Titan is, in many ways, a mirror of early Earth. Not a perfect mirror. The temperature is profoundly wrong, the chemistry is shifted, the energy sources are different. But the processes, atmospheric chemistry producing organic molecules, liquid cycling through a landscape, weather and erosion shaping terrain, these processes are Earth-like in their mechanisms, if not their materials. Some scientists have described Titan as an early Earth in deep freeze, a world where the prebiotic chemistry that led to life on Earth is playing out, but at cryogenic temperatures so slowly that the results are spread across billions of years instead of hundreds of millions. This is almost certainly an oversimplification, but it captures something important. Titan is doing chemistry, complex organic chemistry, in a natural environment with natural energy sources over geological timescales. The products of that chemistry are accumulating on the surface in quantities that we can actually go and measure on Earth. Whatever prebiotic chemistry occurred before the origin of life has been completely destroyed by life itself. Living organisms consumed the prebiotic soup, evolved, diversified, and transformed the planet's chemistry so thoroughly that we can't reconstruct what the starting conditions looked like. The evidence is gone, eaten by its own descendants. On Titan, the chemistry is preserved. The tholins are there, on the surface, waiting to be analyzed. If they contain the same kinds of molecules that were present on early Earth, amino acids, nucleotide bases, lipid-like compounds, it would tell us that these molecules form readily under a wide range of conditions, that prebiotic chemistry is not a rare accident but a natural consequence of organic chemistry in an energized environment. It would make the origin of life seem less like a fluke and more like an inevitability. And that would have profound implications for the Fermi paradox, the question of why. If life arises easily, we don't see evidence of it elsewhere in the universe. If Titan shows us that prebiotic chemistry is common, then the hard step in the origin of life, the step that's so difficult it might happen only once in the history of a planet, isn't the formation of building blocks. It's something else, the formation of self-replicating molecules, perhaps, or the development of a genetic code, or the transition from chemistry to biology, whatever it is. The building blocks are easy, the assembly is hard, or maybe the assembly is easy too, and we just haven't looked in the right places. Maybe Titan's seas are full of methane-based organisms, simple and alien, going about their business in the dark, cold liquid, completely indifferent to our curiosity. We don't know. That's the point. We don't know, and we should find out. Let me talk about the practical challenges of exploring Titan, because they're formidable and they shape everything about how we approach this world. Distance. Titan is, on average, about 1.4 billion kilometers from Earth. At the speed of light, a signal takes about 70 to 90 minutes to travel from Titan to Earth, depending on the relative positions. This means that real-time control of a spacecraft on Titan is impossible. There's no joystick, no remote control. By the time you see what the spacecraft sees, the scene is already over an hour old. But by the time your command reaches the spacecraft, another hour has passed. A round-trip communication delay of 2.5 to 3 hours means that everything the spacecraft does must be either pre-programmed, or autonomous Dragonfly is designed for high autonomy. Its flights will be pre-planned, the route programmed before launch, with updates sent during the cruise phase and during surface operations. But the moment-to-moment flight control will be handled by onboard computers. Dragonfly will navigate using inertial measurement units, radar, altimeters, and cameras. It will avoid obstacles autonomously. It will select landing sites based on terrain analysis done by its own software. It will be, in a very real sense, a robot pilot flying itself through an alien sky. The communication challenge doesn't end with delay. Titan's distance means that the data rate, the speed at which information can be transmitted, is very low. Dragonfly can't stream high-definition video back to Earth. Each image, each spectrum, each data packet must be compressed, prioritized, and transmitted slowly over hours or days. The total data return from the entire mission will be a tiny fraction of what an Earth-based drone could transmit in minutes. Every bit is precious. Temperature, minus 179 degrees Celsius, 94 Kelvin, is cold enough to cause serious problems for spacecraft electronics. Semiconductors behave differently at cryogenic temperatures. Batteries lose capacity. Lubricants solidify. Metals become brittle. Rubber seals lose flexibility. Dragonfly's design must account for all of these effects. And the MMRTG, the nuclear power source, does double duty, providing not only electricity, but also waste heat that can be used to keep critical components warm. The atmosphere. Titan's atmosphere is dense and opaque, but it's also dynamic. Winds, turbulence, and atmospheric density variations can affect flight performance. Dragonfly's flight control algorithms must be robust against wind gusts and turbulence, conditions that are difficult to predict and impossible to test in advance on Earth. Wind tunnel tests have been conducted using nitrogen gas at Titan-like pressures and temperatures, but no wind tunnel can perfectly replicate Titan's atmosphere, and the actual flight conditions may include surprises. The surface, Titan's surface material, is not well characterized. The Huygens landing site was soft. The probe sank into the surface, but other areas may be harder or softer, rougher or smoother. Dragonfly needs to land safely on surfaces that haven't been surveyed at high resolution. The radar altimeter will provide terrain data during descent, but the choice of landing site will always involve uncertainty. A rock hidden in a tholin drift, a slope that's steeper than expected, a surface that's too soft to support the lander's weight. Any of these could cause problems. And then there's contamination. This is a concern that applies to any mission searching for signs of life. If Dragonfly carries terrestrial organic molecules on its surfaces, and it will because complete sterilization is impossible, those molecules could be mistaken for Titan native organics, or they could contaminate the very materials the instruments are trying to analyze. The mission team is taking extensive precautions to minimize terrestrial contamination, but zero contamination is not achievable. The data analysis will need to account for potential terrestrial contributions, distinguishing Earth molecules from Titan molecules based on isotopic signatures, molecular distributions, and other criteria. I want to step back and talk about what Titan means for the future, not just of planetary science, but of human civilization's relationship with the solar system. Titan is, in some respects, the most habitable world in the outer solar system for humans. Not comfortable, obviously not, but habitable in the sense that the environment, while hostile, is not as immediately lethal as most other bodies. On the Moon, a spacesuit leak is death within minutes. On Mars, the atmospheric pressure is so low that your blood would boil at body temperature without a pressure suit. On Titan, the atmospheric pressure is higher than Earth's. A suit leak would not cause explosive decompression. You'd freeze and you'd suffocate from lack of oxygen, but you'd have time, minutes possibly, to patch the leak. The thick atmosphere also provides radiation shielding. Cosmic rays that would reach the surface of the Moon or Mars are absorbed by Titan's dense atmosphere. An astronaut on Titan's surface would receive less radiation than an astronaut on the International Space Station. The dense atmosphere also means that flying is easy, not just for drones, for human aircraft. The combination of thick atmosphere and low gravity means that a human with wings strapped to their arms could in principle fly under their own power. The physics works out. The The required muscle power is within human capability. I'm not saying anyone will strap wings on and fly through Titan's methane-scented air, but the fact that it's physically possible is delightful. The fuel for a return trip could theoretically be manufactured on Titan. The atmosphere contains methane and nitrogen. Methane can be used as rocket fuel. SpaceX's Raptor engines burn methane. The surface contains water ice, which can be electrolyzed into hydrogen and oxygen. The raw materials for propellant production are abundant. Isaru in situ resource utilization is more straightforward on Titan than on almost any other body in the solar system, because the resources are literally lying around on the surface and floating in the atmosphere. Of course, getting to Titan is enormously more difficult than getting to the Moon or Mars. The travel time, 7 to 8 years, makes human missions impractical with current propulsion technology. Nuclear thermal propulsion could potentially reduce the travel time, but it's still being developed and is decades away from human-rated status. Titan will be explored by robots for the foreseeable future. But in the very long term, thinking in centuries rather than decades, Titan is one of the most promising locations for a permanent human presence beyond Earth. Its resources are abundant, its atmosphere provides protection and buoyancy, and its distance from the Sun, while extreme, is not necessarily a disadvantage if nuclear energy is available. Some space visionaries have even suggested that Titan could be the launching point for exploration of the outer solar system and beyond. Its low gravity makes launch from the surface relatively easy. Its atmospheric resources enable propellant manufacturing. It could serve as a fuel depot for missions to the Kuiper Belt, the Oort cloud, and eventually the stars. This is wildly speculative. No one alive today will see a human settlement on Titan, but the possibility exists, and the science we do now with Cassini, with Huygens, with Dragonfly is laying the groundwork for decisions that future generations will make. There's one more thing I want to talk about before I let you go, and it's something that I think about every time I look at images of Titan. Titan is beautiful. Not in the way that a sunset is beautiful, or a mountain range, or a coral reef. It's beautiful in a stranger, quieter way. It's the beauty of an alien world that reminds you of home. The images from Huygens, that dim orange landscape, those rounded ice cobbles on a dark plain, look like a beach at twilight, not any specific beach. The idea of a beach, the archetype, a place where land meets liquid, where the sky meets the horizon, where the air smells of something unfamiliar but recognizable. The radar images from Cassini, those branching channels, those coastlines, those dune fields, look like aerial photographs of Earth rendered in an alien color palette. You could show someone a Cassini radar image of Titan's coast, and without context, they might think it was a satellite image of Scandinavia or the Canadian Arctic. This resemblance is not a coincidence, it's a consequence of physics. The processes that shape landscapes, erosion, deposition, wind, fluid flow, impact, operate according to the same physical laws everywhere in the universe. The specific materials differ: water versus methane, silicate rock versus water ice, quartz sand versus organic tholins, but the physics is the same. Gravity pulls fluid downhill, fluid erodes soft material and deposits it in low-lying areas. Wind sorts particles by size and shapes them into dunes. Impacts create craters. These processes produce similar landforms regardless of the planet, because the physics doesn't change. This universality of physics is one of the deepest truths we've discovered about the universe. The same laws that govern the flow of water in a Colorado River govern the flow of methane in a Titan channel. The same equations that describe the formation of sand dunes in the Sahara describe the formation of tholin dunes near Titan's equator. The universe doesn't have special rules for Earth and different rules for Titan. There's one set of rules, and they produce landscapes that, despite being made of alien materials at alien temperatures in alien environments, look hauntingly familiar. I find this beautiful. Not just aesthetically, philosophically, it means that the universe is comprehensible, that the things we learn here apply there, that the physics we discover in our laboratories and our classrooms is not parochial, it's universal. When we send a drone to fly through Titan's atmosphere, we design its rotors using the same aerodynamic equations that describe a helicopter on Earth. We predict its flight characteristics using the same fluid dynamics. We calculate its trajectory using the same mechanics. The universe is consistent, and Titan is proof. We are about to send a nuclear-powered helicopter to an orange moon 1 billion miles away, where it will fly through an atmosphere thicker than Earth's land on a surface made of organic molecules and search for chemistry that might be a precursor to life. It will fly over dunes made of plastic-like particles, past lakes of liquid natural gas, toward a crater where water and organics once mixed in conditions that might have sparked something extraordinary. This is actually happening. It's not science fiction, it's a funded, approved, under construction NASA mission, with a launch date and a flight plan and a team of engineers and scientists who have devoted their careers to making it work. The spacecraft is being built right now in a clean room at the Johns Hopkins Applied Physics Laboratory in Maryland. Technicians in bunny suits are assembling the instruments, testing the rotors, integrating the MMRTG. Software engineers are writing the code that will fly the drone autonomously through an alien atmosphere. The mission planners are mapping the flight path. 36 planned flights, each one a leap into the unknown. And in 2028, if all goes well, a rocket will launch from Cape Canaveral carrying a small machine with 8 rotors and a nuclear heart aimed at a dot of light near the rings of Saturn. It will coast through the void for 8 years, a tiny artifact of human curiosity, alone in the dark, carrying with it our questions about chemistry and life and the nature of the universe. It will arrive at Titan in the mid-2030s. It will plunge into the orange atmosphere. It will deploy its parachute and descend through layers of smog made of molecules that might, under different circumstances, have been the ingredients of living things. It will reach the surface and settle onto the dark, organic, rich terrain of the Shangri-La dune field. And then it will fly. A human-made machine flying through the atmosphere of a moon of Saturn, landing, sampling, analyzing, taking off, flying again, hopping across a landscape that no human eye has ever seen at ground level. Heading for Selk Crater, where water once flowed on a frozen world and where the answers to questions we've been asking for centuries might be waiting in the chemistry of the surface. What will it find? I don't know. Nobody does. That's the point. That's the whole point. We're going to Titan because we don't know what's there. We're going because the questions are too important not to ask, and because the only way to answer them is to go. Will it find signs of prebiotic chemistry? Probably. The atmospheric models and laboratory simulations strongly suggest that the tholins contain complex organic molecules. DRAMs will characterize them in detail, and the results will tell us something profound about the universality of organic chemistry in the solar system. Will it find signs of life? Probably not. The odds are long. The evidence is ambiguous. The hypothesis of methane-based life on Titan is scientifically sound, but empirically unsupported. Dragonfly might find something surprising, an unexpected chemical signature, a pattern that doesn't fit abiotic models, and that would be thrilling. But finding definitive evidence of life on Titan would require extraordinary data and extraordinary scrutiny, and a single mission is unlikely to provide both. What Dragonfly will do, what it's designed to do, is transform Titan from a world we've glimpsed through haze into a world we've touched and tasted and measured at ground level. It will give us context, it will give us ground truth, it will take the blurry radar maps and the distant spectra and the tantalizing models and anchor them in reality, and it will fly across dunes and between lakes, over ice mountains and down into crater floors, from site to site, sampling the surface of a world where methane rains from an orange sky onto beaches of organic sand. 170 kilometers of flight on a world where no machine has ever flown, no wheel has ever rolled, no human foot has ever stepped. The human urge to explore, to go to places we've never been, to see things we've never seen, to ask questions we can't yet answer. This urge is what put 12 people on the moon, 5 rovers on Mars, and a probe on the surface of Titan. It's what's building Dragonfly right now in a clean room in Maryland. It's what drives the scientists and engineers who spend decades of their careers on a single mission, knowing they might retire before the spacecraft reaches its destination. Titan doesn't care about us. It doesn't know we're coming. It has existed for 4.5 billion years without any awareness that a species of primates on a small rocky planet in the inner solar system has been staring at it through telescopes, sending robots past it, dreaming about it. But we care about Titan. We care because it's there, because it's strange, because it has rain and rivers and seas, but not of water, because it has chemistry that might be teetering on the edge of life, or might have nothing to do with life. And we can't tell the difference from here, because it challenges everything we think we know about what's possible in this universe. Titan is a world made of questions, and we're going there to listen for answers. Thank you for spending this time with me. I know it was a long journey, almost as long as the real one, but Titan is worth the trip. Even from here, even in words, even in imagination. The real trip starts in 2028, 8 years of flight. And then a drone in an orange sky on a world where it rains liquid natural gas, where the sand is made of the building blocks of life, and where the biggest question in science might be answered by a small machine with 8 spinning rotors and a nuclear battery flying through an alien atmosphere. Alone, I'll be watching. I hope you will too. Good night.